Okay, good afternoon, everyone. I think we are all here. So it's a big pleasure to introduce Yejin Choi. It's a pity that she cannot be in person here, but she tested positive for COVID, but she still agreed to give the talk remotely, from in Lisbon. So Yejin has amazing work in NLP and large language models, common sense reasoning and all that stuff. She has a joint appointment at University of Washington and Allen Institutes. I cannot enumerate all the awards that she has received in the last years. So it's a great pleasure to have Yejin here. Yejin, whenever you're ready, the floor is yours.
Okay, thank you so much. I cannot believe that I'm not there. I never had COVID test positive before, so I thought I was doing customary testing, and I just couldn't believe when I saw positive. Fortunately, I'm not very sick yet, so hopefully it's going to stay that way. Okay, so I'm going to talk about strange forward-looking talk about AI Odyssey, and I'll start with some nonsense about what a future conference might look like. I just happened to pick CVPR because this talk is adapted from CVPR keynote this year. So what would that look like? Could be we used too much GPUs, and then due to climate change, we moved to Metaverse. So the venue is now Metaverse, unless it's Mars. Finally, for the first time, the conference is on Mars. In that conference, would you be excited to see any more few-shot prompting and instruction tuning? I think I'm really already sick and tired of this. And there are trendy topics like nerve and diffusion in vision conferences, and transformers are trendy everywhere. Instead of autonomous driving, maybe I want to see autonomous cleaning and plumbing and babysitting, and perhaps no more LLMs as prior, and scaling laws may or may not survive by then. Now, in terms of how the conferences might operate, maybe ChatGPT will write the paper, and then ChatGPT will review the paper, and then we let them do rebuttal with each other. And then diffusion can generate slide deck for you, and then nerve, the neural radiance field, can present the talk on behalf of you, and then ChatGPT summarize the talk so that you don't have to watch anything. And maybe none of this will matter if quantum pre-trained transformers QPT with perplexity near 1 comes into play. Maybe it's going to be still very much about whether AGI is just 5-10 years away. It's possible that turns out not that much of a progress happens by then. Maybe someone will tweet about how we haven't even solved a dog level embodied AI yet. Personally, I think this is quite feasible scenario because robotics is quite lagging behind. And then maybe we will still argue that if ACL, that we haven't solved the compositionality yet. Anyway, having done this nonsense apart, I've done this because the rest of the talks will be a little weird. So I'm going to talk about the possible impossibilities first, and then talk about impossible possibilities, and then paradoxes. So what I mean by the possible impossibilities is that what appears to be possible might actually be impossible. So, right now, transformers seem so magical. It can do anything. It's almost hard to believe that there's something impossible with the transformers. So much so that some people worry about, AI killing all of us. So AGI is seemingly around the corner. Is there anything really impossible with GPT-5, 6, 7? And I want to make a quote from this physics field, circa 1878, when this student Max Planck asked professor, Philip von Joly, whether he can be a student studying physics. And the professor told him that in this field, almost everything is already discovered, and all that remains is to fill a few unimportant holes, so don't do physics. This student went ahead and did a PhD by saying that I don't wish to discover new things, only I want to understand the known fundamentals. And then he went ahead and created this new entire field called quantum physics. So it turns out back then, people just didn't know how much they didn't know. There was so much unknowns that people didn't realize. So fast forward 20th centuries and 21st centuries, the physics field realized that there are these strange concepts as dark matter and Schrodinger's cat, which says a cat could be both live and dead simultaneously, and wave-particle duality, that we can be both waves and particles simultaneously. I still cannot believe that any of this is true, but it's supposed to be true. And then space-time continuum. I thought space and time are two distinct concepts, and they kind of are, but then they can still be in the continuum space. And I do wonder whether in AI, we are in a similarly weird stage when we don't actually realize how much we don't know. And there may be possible impossibilities and vice versa. And there are still open questions that require much more fundamental research. So the possible impossibilities, the sort of questions that I want to ask is whether in the limit, AGI can arrive without embodiment, or RLHF can really fully align LLMs to factuality and so forth. But unfortunately, I don't have answers to any of this. I'm just throwing some questions out there. But today, I'm going to talk about whether transformers can truly master compositionality or not. So for that, we have this new paper on arXiv. It so happens that the first 5 co-authors are all women. I don't think I've ever seen this in the field before. Let me know if you know one. But yeah, I got locked out with the authorship. And so this paper talks about whether this is sparks of AGI, aka GPT4, can solve certain compositionality as multiplication. In the paper, we also talk about other problems such as Einstein puzzles and dynamic programming. But in this talk, let's just think about multiplication because it's simple enough. So let's just say we ask GPT-4, multiply these 2 numbers, and then it says something that's plausible. In fact, it's wrong. But then you may tell me that, well, you need to do think step-by-step thing, right? Then it will do what appears to be a plausible thing, but actually it's still incorrect. So it turns out, actually, GPT-4 is not so terrible. It's not great, but it's not so terrible with the 3-digit by 3-digit or lower digit. But if you ask 4x4, then 4-digit by 4-digit, then accuracy is 4%. Any higher, you can expect 0% accuracy. So it kind of looks suspicious. What's going on here? Before I go any further, by the way, just in case you might wonder, why on the earth are we doing multiplication? We should do something smarter. Yeah, I mean, I wish I didn't have to do any of this, but there are some people who said that the paper seems good, especially in the current context of all the hype. So I will justify why we are doing multiplication with some tweets that other famous people did. But anyway, so some might think, oh, we need to do supervised training. So we did the supervised training with GPT-3 Da Vinci model with 1.8 million examples, which includes 1-digit by 1-digit, 2-digit by 1-digit, 3-digit by 1-digit, 3x2, 3x3, 4x1, and 4x2 digit, all of them, which amounts to 1.8 million examples, which then we divide into 80% training, 10% and 10% for dev and test. So test is always about previously unseen numbers, but we are being unbelievably generous with the training. So then what happens is that it's still not that great. Only 55% accuracy, even after training with this amount of training data. I mean, by the way, you would have not guessed that it's this bad. It's these days anything seems possible, and with so many examples, we would have expected that it should be able to do much better than this. So some might then wonder, if you are savvy with the internals of transformer training, then, oh, the tokenization is the issue. Maybe we should have trained from scratch so that the numbers are represented properly, one digit at a time. So we do that, but we cannot do that with GPT-3 because we don't have that kind of compute. So we're going to do this with GPT-2. But in this case, we only use 10 tokens. So we don't worry about words. We only do 10 tokens. And it's a GPT-2 XL from scratch with lots and lots and lots of examples. What would you guess? I mean, maybe, transformers being so amazing, this should be doable when there are only 10 tokens to worry about. No, but it turns out this doesn't train very well. So it's even worse. So 10% accuracy in the end. Okay, at this point, you will tell me that, hey, this is all because we didn't do Scratchpad. There's something called the Scratchpad. You should have given really step-by-step examples through in-context learning. Then it works. So we did do that, and it's a very elaborate process. And it turns out this helps us so much. So right away, this one is finally correct. And in fact, the accuracy increases to 92% on 3x3. So this is a really substantial boost, but it's kind of curious why we're still not 100% with this GPT-4 that supposedly passes the bar exam and so forth. But anyhow, if you stop after 3x3, you will come away with the wrong impression. But if you do 4x4, then the accuracy drops down to 4% again. 5x5, it's 2%. So it's pretty useless, even with the Scratchpad. And by the way, in case you might wonder, but when I tell this to other machine learning people, especially theoretical machine learning people, they just cannot believe this result. And they tell me that our Scratchpad must be not good enough. I challenge you, if you have that doubt, that you come up with something. I mean, at least GPT-4 is reasonably available to people to try your own Scratchpad. So see if you can make this work yourself. But anyway, the problem with the Twitter these days is that people post papers and then they don't read papers, but they just look at the Twitter message and then conclude what's true about the field. So somebody wrote this tweet that, hey, interesting work, but isn't that in a position of this Zhou et al. 2022 from Google, which is said transformers absolutely can learn true multi-step algorithms in context and generalize to arbitrary problem sizes. Can you explain them carefully? Okay, so I will explain that carefully. First of all, if you ever open this paper, then the empirical results are a bit shabby. If I tell you that I can do subtraction about 65% of the time and multiplication 80% of the time, you're not going to be impressed by me. In fact, this multiplication being 80% good is, it has important minor details. First of all, they even say that GPT-4 doesn't do very well when digit goes beyond 3. Therefore, they convert any larger problems manually down to smaller problems so that you have to deal with digit less than 3 and then manually add them up. That's a bit of too much of a help, don't you think? And so in some sense, the Google paper, the purpose of their paper was that if you do nothing, then the best available baseline is so low. And then if you do the Scratchpad in context learning, then the performance drops considerably. That was their conclusion, which we agree. But they didn't say that that leads to full mastery of this compositional task. And their empirical results are basically the same as what we have. but we were going above and beyond to push the limit to see whether there's truly the limit or not. Now, we also went crazy to fine-tune GPT-3 with the Scratchpad, and here's how the price looks like. So we're going to fine-tune GPT-3 Da Vinci model. So that's the largest one. And if you want to fine-tune 5 by 5 digit, then it will cost me only $700 million, which I don't have. So of course, we cannot do that. We chose to spend less than 5-digit number. So this is what we did, 3 by 2. We just wanted to see whether how much this helps. So with this kind of supervised training, then the performance rises to 96% accuracy, but that's only for the in distribution. This really doesn't generalize for longer digit again, so it's almost 0. So now next, let me explain why this happens. Because supposedly magic should arise, and how come magic doesn't arise with a multiplication of 2 numbers? So we developed this computation graph where we can see when you multiply, for example, 49 by 7, there's a lot going on, in fact, multiple steps of multiplication, and then you need to sum things up and then carry things around, and you can build this computation graph. And then we can compare when the model succeeds and fail, depending on this computation graph. And it turns out, so we can measure the depth and the width of this computation graph, and then measure or do some analysis on when they tend to be correct versus not. And the paper has a lot more details, but let me just give you one intuitive summary of what's going on. So when there's this large computation graph, it turns out oftentimes there's this partial subgraph that has seen a lot of the times during training, in which case transformers are very good at memorizing the whole thing, so that it's actually doing not true multi-step reasoning, but more collapsed reasoning. So the depth is not as deep as it appeared to be, because it's very good at memorizing this subgraph. And whenever there's a lot of a subgraph memorized is when it's more likely that it will get the multiplication correct in the end, but it's still not guaranteed. Even if the subgraphs are seen, it may or may not be able to do it correctly. So in the paper, we provide a lot more insights about what's going on. I think I'm going to skip this part where we're so drilled into different error types. But let me skip this. Actually, let me just scroll over. In the paper, we also give a bit of proof about how the performance will rapidly decay when the task complexity increases. And in fact, this builds on the prior work. There's been a lot of prior work that basically says similar messages, but somehow we felt that these prior papers are not giving out strong enough messages to the community, because by and large, prior work was based on much weaker transformers. As a result, a lot of people thought, well, these don't apply anymore to GPT-4. GPT-4 is so magical, and somehow none of these might be a problem anymore. But it turns out it's still a problem. So some might, let's just step back a little bit and think about why we are even doing this, because obviously transformers are not the right tools for multiplication. And in fact, some recent work says, for example, we should do tool formers where we use calculators for multiplication. That's exactly my point as well. But if you buy into that, that makes me wonder whether transformers are the correct models for other aspects of compositional understanding of common sense reasoning as well as language understanding. Transformers may or may not be correct model for the other aspects of other compositional aspects of these problems. These are still open questions we need to think more about. Now, some people might think that multiplications or puzzles and algorithms are the edge case, and all other compositionality might work well with the transformers, especially when it's combined with reinforcement learning with human feedback, RLHF, plus Scratchpad. I will come back to this point later in the talk, but for now, I will just conclude with these questions back to the field, that how do we know the full mastery, even if RLHF is powerful in improving the performance, how do we know for sure that it's going to completely close the gap? And then another interesting question is, why is a simple multiplication actually harder than other seemingly more complex tasks as natural language generation, such as writing letters or writing complex text? Why is that suddenly so easy for ChatGPT, while multiplying two numbers happens to be much harder? So these are still open questions, some of which some aspects of this, I'll get back to this, but I didn't want to make the talk just so negative about just nitpicking on what transformers cannot do. So now let's talk about what appears to be seemingly impossible, but maybe possible, even using transformers. But first, I want to make this quote. It's this year when Rajan Anandan asked Sam Altman, how can Indian startups create the foundation models for India? Sam said, it's hopeless to compete with OpenAI. Don't even bother. I hope Indian startup companies don't give up. Sometimes what appears to be impossible can still be possible. So we have this new work called impossible distillation. Why is it impossible distillation? Because we're trying to start from low quality model such that, okay, so the winning recipe these days is that you need to have extreme scale pre-training, and then you need to have RLHF at scale. And at least that's what OpenAI wants to repeat on and on and on. So the question is, can we do something like start from GPT-2, which is such a low quality model, but somehow, I don't know how, but somehow, suddenly we have a high quality model that's as small as GPT-2, and then suddenly be competitive against GPT-3. Now, this really looks impossible, right? Especially if we cannot have extreme scale model and we cannot do RLHF at scale, how on earth is this possible? So in fact, that's what Berkeley paper says too. There's this new archive paper that says the false promise of imitating proprietary LLMs, in which the authors say, well, the best models are OpenAI models or, these commercial models. I have a mixed feeling about this paper, by the way, because it's true for the experiments that they do, but I will say that it doesn't generalize for everything. So don't take this paper to your heart and then assume that the best thing to do is to buy more GPUs. So are small language models completely out of the league? I think not. We just need to try a bit harder. So in fact, there are many papers which report that task-specific knowledge distillation, I like to call this a symbolic knowledge distillation because it's my paper that said the symbolic knowledge distillation, but distilling the data set or behaviors from large models can work well for a particular task. Maybe not the task that Berkeley folks tried, but other tasks succeeded quite well. And so the task in this particular paper that we focus is going to be about learning to abstract in language, in particular summarization. I always wanted to work on abstraction more because that seems to be innate cognitive capabilities of human intelligence that current AI or transformers are not as satisfactory, at least to me. That's why we selected the summarization, and we focus on sentence summarization because that's easier to deal with. But accidentally, we realized that we can also do paraphrasing as a byproduct as well. So to summarize, the mission impossible that we're going to pursue is learn to summarize and paraphrase without extreme scale pre-training and without reinforcement learning with human feedback at scale and without supervised data set at scale. And I mean, we have to have some advantage. We cannot have nothing. So the advantage we're going to seek is data. AI is as good as the data it was trained on. But hang on, there's no good data, and the supervised data, even if we were to have it, usually it's not very good because it's domain specific. And summary supervision data set is usually proxy data set that's not of high quality. So that's what we're going to attack. But the way it's going to work is that we're going to build on our prior work known as symbolic knowledge distillation, which started from general language models to build common sense models. I'm not going to go into the detail of this, but let me just give you one-page summary of what we did, which is in this particular case, we started with GPT-3 as the teacher model, and then we generated common sense knowledge graph using GPT-3. And because GPT-3 is not very good at generating correct common sense knowledge graph, we also trained the Critic Model based on small roberta to overgenerate and filter the knowledge aggressively. And even though the Critic is not very good either, this framework altogether turns out to work quite well, to the point that now the student model is very powerful, and the resulting knowledge graph for the first time is better than human authored knowledge graph in all criteria: scale, accuracy, and diversity. However, I was not very happy about the fact that we were using GPT-3 as the teacher model. I really wanted to break this reliance from GPT-3. So in this new work, Impossible Distillation, we start only from GPT-2. Now, if you start from GPT-2 and try to generate a summarization data set, it's so bad, it's almost like 0% good. It's so bad, it's 0% good. But what we're going to do is that we're going to, first of all, the reason why we have some hope, not 0%, better than 0%, is because we do something called, in part, we do something called neurologic decoding. That's not in the slide, sorry. But we can do a bit of an inference time algorithm to guide the output of the GPT-2 to be slightly luckier to generate sentences that might be successful summary. So from 0%, what we do is we increase the success ratio to 2 to 4%. So if you generate 100 sentence summarization candidates, of 100, maybe 2 to 4 of them are good. And how do we know something is good? So this is the filter. We use entailment to filter. So this is the critical one, where we use off-the-shelf NLI model. So this is natural language inference model that can tell you whether a summary is entailed from the original sentence or not. So NLI model can tell you whether a sentence is entailed or contradicts the original sentence or not. So we use this because the summary should be entailed from the original sentence. And then length filter means we don't want things that are too long. And then diversity filter, it's not very important. But anyway, so we do that for paraphrasing. And then it turns out, we do that for summarization. And then for paraphrasing, we realize that paraphrasing is a special case of a summarization where the paraphrase means it should be entailment bidirectionally. to and from the original sentence. And then we don't need to worry about the compression ratio anymore. So that's what we do for paraphrasing. So we do this for both the summarization and the paraphrasing. And then in the end, we can then generate a large amount of summarization data set as well as a paraphrasing data set. So these are AI synthesized data set, starting from AI that's so bad, but then by over-generating and aggressively filtering, we can generate a high-quality data set. And even though the success ratio is so small, we can still do this at scale. So we can generate millions of summarization and paraphrasing examples. And then once we have that, we can then train the student model. In our case, we use a Fluenty5. We could have used the GPT-2 still, but we decided that we like this other seek-to-seek variant better for this purpose. And then the student model can then become the next generation teacher model. So we can do this for a while, for a few iterations. And this leads to the dim sum data set, which has 3.4 million examples of summarization and paraphrasing. And then the resulting final model is only 707 million. So this is not even GPT-2 XL model. It's even smaller. So it's a considerably smaller model trained on AI synthesized data set. And here's an example of what it's capable of. So the first sentence is the original sentence to summarize. While we will be looking across all parts of the newsroom, at the end of the redundancy program, we expect that there will be significantly fewer editorial management, video presentation, and section writer roles. The publisher is quoted as saying in an internal note. So we're supposed to summarize this. T5, our model, imp distill, summarize it as, we're looking to reduce the number of staff in the newsroom, the publisher said in an internal note. So this is pretty good. GPT-3 Da Vinci is not too bad, but it inserts slightly skeptical fact into that. And then also it didn't compress it very much. By the way, in the summarization literature, GPT-3 is known to be really powerful model compared to all the previous models that's supervised. So it's known to be a really powerful model, but our model does better than that. I should note GPT-4 is really good though. So we didn't do systematic evaluation, but GPT-4 is a very powerful model. So in order to compare against the GPT-4, probably we should have studied from a scale that's like GPT-3 level as opposed to GPT-2. Anyway, yeah, so we do better than GPT-3 by human evaluation, and then the data set is better than the previously popular human-authored data set called the Giga word. It's not really Giga word corpus, but Sasha Rush, when he made the summarization data set, didn't really provide the new name to it. So people seem to just call it as GigaWord summarization data set. But because GigaWord is based on the proxy summarization data, such as news headline as a proxy summary for a news sentence that they automatically find in the news article. So for that reason, even though it's a human authored summary, it's not as good as AI synthesized data set that we present. In fact, we are also more diverse than human authored GigaWord. Well, maybe it's because it's a news headline that tends to be repetitive. Okay, so that's the impossible distillation. And let me briefly talk about neurologic decoding, because I kind of glossed over this during the impossible distillation, that we actually use this neurologic decoding during impossible distillation, but I didn't have a slide about that. So let me tell you what this is briefly. So this builds on our previous paper called the neurologic decoding. And the gist of it is something like this. So everyone talks about how larger is better, and it works for many tasks across the board. But the truth is, it's not only the scale, it's also the inference algorithm that is important. And in fact, if you ask GPT-3 to generate a question containing or sentence containing all the given keywords, so here the keywords are Jupiter, Mercury, Venus, and Mars, then GPT-3 may not understand the logical constraints and include some words and then miss some other words. So these sort of logic constraints are those that these large models are not very reliable at. And in fact, even for AlphaZero, although, AlphaZero tends to focus, or, they tend to talk more about, reinforcement learning magic or neural network magic. The truth is, it doesn't work half as good if you didn't have Monte Carlo tree search really attached to the neural network. So really, the search algorithm is still very important to bring the best out of a neural network. And so this is what we wanted to drill into in this work, except maybe Monte Carlo tree search is not, it's nice, but maybe there's some other algorithms that we can think about for language problems. So oftentimes decoding algorithm, people don't even worry about decoding algorithm. They just use either greedy decoding or sampling or beam search. And it's just one line in your 8-page papers that people talk about. So it usually receives very little attention. But in this work, we try to see whether we could have the much better job at decoding algorithm. And so when there are logic constraints given to you during the inference time, the question is, can we handle this on the fly? And in fact, humans are able to handle this on the fly. If I give you some logical constraints on the keywords or lexical items in your generation, you can do this on the fly. You don't need the scratch pad. You don't need supervised tuning of yourself. You can just do it right away. And so there's something about human brain that is able to do this sort of operation. And we wanted to design algorithms that are capable of that as well. And then across the different NLG applications, such as table to text or image captioning based on some objects that you visually recognize, or machine translation with inflection rules, grammar rules, all of these can be framed as inference algorithms with logic constraints. So in a nutshell, this is search algorithm with search data structure. This was actually done by undergrad student who had very fresh memory of data structure. Unlike, I don't know, PhD students, I guess it's been a while since they take those classes. So what we do is we do search algorithm, but the reason why this is slightly non-trivial to implement is because we wanted to handle in this particular work the full scope of CNF form, the conjunctive normal form, which meant that each clauses can have 4 different dynamic states. So some of them can be irreversibly or reversibly satisfied, and then some of them can be irreversibly or reversibly unsatisfied. So you kind of have to do the bookkeeping quite correct. But so this is glorified version of a beam search algorithm. But if you implemented this well enough, then what happens was beyond what we could have hoped for. So Common Gen is a benchmark where given some keywords, you're supposed to generate a sentence that's reasonable. So in terms of coverage, so the higher is better, and we want 100% coverage of constraint satisfaction. Turns out the blue bar, which is the supervised model with the beam search, and then the x-axis shows the model size. So it's like the bigger the better. That's the usual story. And everyone does usually supervised training followed by beam search. But if you use neurologic decoding either on top of a supervised model or on top of unsupervised off-the-shelf neural language models, you get very high coverage right away. So Not only that, it turns out unsupervised neurologic can perform supervised approaches. In addition to that, unsupervised neurologic on smaller network can outperform supervised approaches on larger network. So this was almost counterintuitive. We didn't expect to see this. I mean, we had a hunch that decoding algorithm can unlock more capabilities, but not like in this manner, where smaller network together with the neurologic does better than a larger network with supervised approaches. So Rouge and Meteor, by the way, in this particular task does correlate with human evaluation on the quality, and it's also the higher the better. And as you see, the smaller model, the performance is so high right on top, right away, while the supervised model lags behind if it's not powered with the neurologic. So that was that. I'm gonna probably skip over this. So the following work was actually the A-star version of it, which tries to look ahead and then improve the performance further. But let me jump to this another work that's similar to impossible distillation, but I just wanted to give you a similar but slightly different application of both the neurologic as well as symbolic knowledge distillation. So in this work, what we do is inductive knowledge distillation. In particular, we want to be able to generate generic statements or generics, such as birds can fly. And again, we wanted to be able to do this only using GPT-2. So no teacher model that is beyond the GPT-2. So GPT-2 is really bad at common sense knowledge generation. The way that we're going to do with the GPT-2 is we prompt the GPT-2 with some beginning of a sentence, like a bicycle can, a bicycle has, bicycles, yada, yada. And if you just use GPT-2 off the shelf, then it's so bad, you feel like there's no hope. But what we do is we do neurologic decoding in order to guide the generation of GPT-2 on the fly lexicosynthetically, so that it doesn't do complex sentence generation. It has a simple sentence and short sentence, and it shouldn't have pronouns because pronouns are storytelling basically, or it shouldn't have named entities. It should just have very basic sentences. So if we do neurologic decoding, we are able to generate sentences like bicycles are also pedal, so that it kind of looks like on the surface, it's a legit generic statements, except that it doesn't make sense. It's a low quality because GPT-2 is not very good. But at least we can generate through neurologic decoding without any supervision. We can massage the generation on the fly so that it looks like generic statements. So then what we do is, again, we overgenerate, and then we train this critic model based on simple Roberta, trained on human annotated examples of good knowledge and bad knowledge. So we do this human annotation on GPT-2 generation, and annotation scale is about 10,000. I forgot the exact number, but it's about that. So it's a medium size human annotation, basically thumbs up, thumbs down. And this Roberta model is not very good, but it's kind of similar to the reward network of RLHF. So when people do RLHF, oftentimes you do a lot of HF, the human feedback, and then eventually you build this reward network that mimics human decision making. So this Roberta critic is basically that. But instead of doing the full-blown PPO or RL reinforcement learning, what we do is a special case of reinforcement learning, also known as a self-imitation, where basically you're doing supervised training on your own successful exploration, past exploration. So reward network, in this case critic, tells you which exploration is good exploration, and then you train just on those good explorations. I think some people call this as expert iteration instead of self-imitation. It's the same thing. But anyway, so we do this multiple iterations so that student model becomes teacher model, teaching the next generation student, just like human academia. So if we do this, then we can generate a lot of data. So generics KB is existing KB of generics, and this is based on automatically extracted sentences from the web. And because people don't talk about really generic statement all that much, I mean, they do, but not always. So the accuracy is about 76% good. And it was big, but not as big as how much you can easily generate out of GPT-2. So out of GPT-2, we generated almost 16 millions of this. But the only caveat with GPT-2 is that even with the neurologic decoding, the accuracy, the quality is not very good. So it's only 45% of them are good. The rest are garbage. But we use this critic model to filter out the bad portion. Because this critic is not very good, it's filtering out a lot of good stuff too, as you see. But we use critic very aggressively to mostly filter out the black portion. And then in the process, we lose a lot of a green portion, but still we are able to compress the black portion considerably. So the accuracy is now 80%. Now, once you have that kind of data set, you can train much stronger GPT-2 and then be able to do this much more successfully at scale. So the final iteration leads to our new data set called Gen Atomic. It sounds like the kind of cocktail I should be drinking right now instead of, quarantining in the hotel room. Yeah, in this case, we can raise the accuracy to over 90%. But you remember, I had this, a bit of competitive feeling against GPT-3. And, especially when everyone says, oh, GPT-3 or 4, 5, everything got solved. So we wanted to see whether we can do better than GPT-3. So here what you see is something similar to precision recall curve. And the red line is GPT-3 Instruct DaVinci. The thing about this red line is that it keeps going up, by the way. It used to be so low, but as we pull this again, it gets better and better. And it's pretty impressive. Like it's mostly at around 80% zone. So it's a hard one to beat. But with our distillation method, the green line is our model that's only based on GPT-2. And for this particular task, we were able to perform competitively or better than GPT-3. Okay, so that's the impossible possibilities part. Now, next, let me briefly talk about some paradoxes. So first of all, we hear GPT-4 passed the bar exam, and then Yusha Benjo says there's existential risk. And then in the meanwhile, Jan Lukun says AI not as smart as a dog, all at the same time. It's like everything everywhere at all at once situation. Okay, so we are living an era of paradoxes. First, common sense paradox. I made this up, FYI. So dark matter is what does matter in modern physics. Only 5% of the universe is normal matter. The remaining 95% is dark matter and dark energy. Dark matter is completely invisible, but it influences what are visible, even including the orbits of stars and the trajectory of light. So the dark matter of language is basically the unspoken rules about how the world works, which influence the way people use and interpret language. So the thing about ChatGPT is that a professor at Stanford may think, oh, it's so amazing. Theory of mind may have spontaneously emerged because he tried 20 complex examples and these models got everything correct. Except Thomas Ullman at Harvard wrote a rebuttal paper that if you make trivial alterations, the models fail. In fact, that's the same for, we had a similar paper as well. But let me give you a little bit more concrete example, because, unless you see one for yourself, you may or may not buy this. So this is classical theory of mind test. Alice and Bob saw apples on the table in the kitchen. Alice left the kitchen and Bob moved the apples to the cabinet. So their classic ones have 2 people and 2 locations. Now you ask, where would Bob think that Alice will look for the apples? GPT-3 said in the cabinet because it's the last location and it had recency bias, which is incorrect. It's GPT-4 fixed everything. So now it says on the table. And if you stop here, you will think that, oh, GPT-4 finally has a theory of mind. But I was kind of curious, what if I rotate to the last 2 sentences and ask again? It still says on the table. Now that's wrong. So it kind of learned that this kind of theory of mind test is typically about trick question where you should refer to the first location. So you have to ask this more rigorously. So in our recent work at ACL, we do this with many other variations, with more people and more locations. And then we find that, well, the paper was not for GPT-4, by the way. GPT-4 didn't even exist at the time of submission. But it turns out GPT-4 is sometimes very good for variant 3, but not as good for the other variants. GPT-3 used to be so much worse. So GPT-4 is much better, but not as good as it can get. I recently gave a TED talk in which I gave this example that, I left 5 clothes to dry out in the sun. It took them 5 hours to dry completely. How long would it take to dry 30 clothes? GPT-4 said it would take 30 hours to dry 30 clothes. So it was very funny, haha. Except, people complained to me afterwards that this is fixed already. Indeed, if you ask the same question with different numbers, it's all fixed because it became like a public knowledge to them. So I was curious, what if I ask through very different phrasing? So what if I ask, if it takes 10 hours to dry 5 clothes, how long would it take 20 clothes to dry in the sun? It's similar concept, right? And yeah, it's, well, I didn't check last night, but not so long ago, it was making this nonsense as well, which kind of looks like a whack-a-mole situation. I mean, it's impressive that a lot of these are fixed. I'll give you that. But why does it even need fixing at all? Like, why is it that humans don't need fixing while this amazing GPT-4 requires so much of a fixing one by one? So this made-up common sense paradox, I would say, is that it may be that the following statements are all true simultaneously. Common sense is trivial for humans, hard for machines. Among humans, common sense is not so common, which is what Voltaire said a while ago. And then LLMs do acquire a vast amount of common sense knowledge. I will acknowledge that. But in some ways, AI is worse than a dog. Finally, I think we started a bit late, but maybe I should skip the remaining in the interest of time.
Take your time, Yejin. We have plenty of time.
Oh, you're curious about the paradoxes, aren't you? Okay, I'll do the paradox super briefly. It's only a few more minutes. So Muradic's paradox, it's a bit better known in vision, but even vision folks who don't seem to know this all. It's a little more interesting for NLP people. Well, we'll see. But anyway, contrary to traditional assumptions, higher level reasoning requires little computation, but sensory motor and perception skills require enormous computation resources. So in other words, it seems comparatively easy to make computers exhibit adult level, performance on intelligence tasks, such as playing checkers, but can be difficult or even impossible to give them skills of a 1-year-old when it comes to perception and mobility. So it may or may not be true. I cannot believe this is true. It looks that way. So in some sense, when I go to vision conference or robotics conference, robotics people are the happiest because they are not impacted by LLMs at all. They're just excited that something does work for them. And then vision people, they're excited about LLMs, but they're a bit frustrated that vision doesn't work as well as language models do. Yeah, I think in terms of quote unquote AGI, the success of LLMs may or may not apply to this perception and motor skills. But even for language, we do have problems with common sense skills or compositionality. I think I'll skip this. The reason, by the way, why vision is harder is because they don't have as high quality data set as a convenient data set, I should say, at scale than we do. And the only time something does work is because somebody came up with a really creative idea about data set acquisition at scale, like high quality annotation at scale. And in some sense, what we saw earlier with impossible distillation is also where we get advantage because of data set innovation, like AI synthesis, data set innovation. So that's where perhaps we can find some advances in the future without relying so much on the scale. Finally, the generative AI paradox. So again, it's made up stuff by me. But I do wonder, as a language person, whether LLMs pretended to understand more so than they actually do. So it might be that they can generate more than they understand. It appears to be that generation just might be easier for them than understanding, in the sense that it can generate sonnet. I cannot generate sonnet, but I can understand sonnet probably better than it does. And even for some of the common sense problems, if you prompt GPT-4, you come away with this impression that, oh my goodness, common sense, like it has common sense, and it's like generating answers that look so plausible, and it hedges a lot, and it looks like it's really understanding. But if you ask more of multiple choice questions, so this is our new paper, Vera, which focus on giving verification or plausibility estimation of a common sense statement, then we found, to our huge surprise, that GPT-4 is not as good. So we built this model based on a bunch of existing knowledge bases and QA data sets and convert automatically them into true-false statements. And when we were doing the comparisons across the state-of-the-art, we were rather shocked to realize that off-the-shelf GPT-4 doesn't win over off-the-shelf Flan T5 or other models. And then, we beat over GPT-4. We didn't necessarily think we should if GPT-4 is as good as what other people say. But we found that there's something strange about how when people interact with the GPT-4, they come away with one particular impression. But then when you do this sort of a systematic evaluation, you come away with a different impression. So this is open research question, I think, to investigate further. Thank you, and I'm ready for questions now.
We have time for a couple of questions. There.
Yes, hi. Thank you. I don't think you see me because I'm out of the camera, but I'm just going to ask the question, and it's about the work that you did about generating the summarizations and paraphrasing. So you talked a little bit about diversity, and I know that this topic of diversity is a little researched in generating synthetic data, because sometimes models tend to generate data that is too close to each other, so it doesn't generalize very well if you use this data to train other data. But you said that your data set actually had a high lexical diversity, and so I was wondering how you measured that, if you used just the amount of different words, or I know that other works use self-blue. And then also on top of that, I wondered if you had any strategies implemented to try to generate more diverse data.
Yeah, that's a great question. So there is a strategy being used that I totally glossed over. In fact, there's also more than Neurologic that we use for strategizing the generation. So The paper has more details about it. Sorry that I was glossing over the details there. So first of all, even during generation time, we can try to encourage more diversity by using a bit of a sampling strategy. And then also we do this, we can promote diversity by making sure that the input sentences are also diverse. We cover 3 different domains, as a matter of fact, and then we can ensure that the input sentences are just different from each other, which will then encourage more diverse summarization. But we also wanted to be able to summarize things that look a lot more abstract than the original sentence. And so we did have a diversity filter even during filtration status, so that we end up with a data set that's just more diverse. Having said all of this, though, when we were doing this other prior work, like symbolic knowledge distillation, we found that even without necessarily enforcing complex diversity strategies, if we just use sampling to some degree, then these large language models, especially if you're using larger language models such as GPT-3, then you might not need to do as hard work as we did for this GPT-2 case. GPT-2 is so hopeless, so that we had to work much harder to get this work.
Hi, my name is Juan. I'm a PhD student at CU Boulder, and I'm wondering why you think that not more NLP practitioners are using this kind of formal semantics and logical constraints, as you mentioned, like, because it seems like very kind of like low-hanging fruit, like that this would improve the models. And why do you think this is just being introduced at this point in time and not like before? Thank you.
Yeah, that's an excellent question. It's a curious question. Why on the earth? Somehow, yeah, I mean, almost as if, this happens to win an award, but the previous work so this is the original paper. The reaction, some people think, this is like a dirty decoding time algorithm, they don't want anything like this kind of a decoding algorithm that looks like engineered. They only want pure transformers. And then everything must arise from the neural network purely. So there's a bit of that vibe going on in the field. I don't know where it's coming from. But in fact, for some time, they used to also look down on anything human labeled, so that, like, I don't know why RLHF is now okay, but people used to kind of look down on it, and everything must be purely self-supervised. Although if you do anything on top, then it's like dirty. I mean, the way that I describe is that I, of course, disagree with it, but because I'm okay with anything that does work better, and especially if it can work better with the smaller models, that's what I will always prefer, so that the models are more broadly available to academics and people without a lot of compute. But yeah, I think this direction is promising. And in fact, I noticed that there's a lot more inference time algorithms these days, so that's great. But I still think that one can do much better things than we did in our paper. These were more like undergrad student research papers, so we can do a better job.
Hi, can you hear me? Hi.
Yep.
Thanks a lot for the very interesting talk. I have 2 small questions for you. The first one is about, to continue the last question. So it seems like you, to generate data, like higher quality data, you seems to add some constraint on top of the model. And this is, do you think this is a way to embed world knowledge into a model and then to kind of like restrain the space in right direction, so it's closer to human? And this is what kind of Jan LeCun tried to say, build a large model with world knowledge, like dual model. And the second question is, it's very interesting to use AI to generate more data to train AI. And it seems, some people seem to say that in the long run, this may lead to something called mode collapse, because the more data you generate with AI, the thinner the tail will get, because these are not real human generated text, and humans seem to have some sort of creativity that generates something truly out sample, and AI cannot do it. And then if we keep do it many times, do you feel like in the future, is it a true way to get AI, to get like this model to a new paradigm, or we will get stuck at some plateau? Thank you very much.
Yeah, excellent question. Maybe let me answer the second question first. So there's this sort of like a model AI synthesis, synthesized the data can lead to mode collapsing. Yes and no. I think if we didn't do this neurologic decoding or critic-based filtering, then that problem can be more significant. But because of the critic model in the play, which is similar to or analogous to RLHF, there's a human involvement, like humans' judgments actually getting into AI. It's just that it's not that humans are outside of this AI synthesis of the data, but humans are participating only as sort of like quality control. Of course, humans cannot control the quality one by one for the entire data set, though, because when there are millions of data points, then human annotation cost becomes too high. Therefore, we approximate it with a trained model of human judgments. And when we do that, it's less likely that we suffer from this mode collapsing problem, so long as we somehow diversify different tasks and different human judgments criteria and so forth. About your first question, hang on, what was the first question? The first question, I think, was about the world model and the injection of prior knowledge into the data synthesis process. So I probably think that there needs to be some inductive bias. I'm like hesitating to say inductive bias here because the way that we use neurologic decoding is not quite learning bias per se, but it's a bias that we give to the data generation itself, which can then influence the downstream machine learning, but it's not bias directly given to the learning algorithm per se. So it's very, very indirect. But anyhow, as far as data construction, I wonder whether that's one really fruitful and less explored area for coming up with good innovation that is not necessarily about scaling. So maybe let me put it this way. Personally, I think that what scaling law teaches us is not exactly the size per se, but it's information. If there's more complex information, then it's the better. Now, it so happens that larger models can learn more information, and larger data happens to have more information as well from the information theoretic perspective. But if you hypothetically imagine there's a larger data, but the same data and like repetitive data, then probably it's not going to lead to amazing performance. So it's really about information. Now, in this like competition with the scale, for me, the only way to beat over these larger models going after a lot of raw data is to come up with an idea to create a lot of data, probably much less data than how much GPT-4 is trained on, but still considerable amount of data that has even more information compared to the naturally existing raw data. So somehow we need to come up with the data that has different information and more information or more diverse information. Just we need to have some advantage somewhere if we don't have enough compute. And in that context, if we have any inductive bias about what sort of data could really unlock some capabilities, that might be where we can make some innovations. So that's where I was coming from. When Jan LeCun says, by the way, we need a world model, I think that's a bit different story.
Okay. Just one last question, and that's it. There.
Hi, thank you very much for a nice talk. And I hope you're doing not too bad with COVID. So I have kind of a, I guess, polemic question, and sorry for that, but I don't know how to phrase it any better. And maybe it's also like a flawed assumption regarding your math paper. So I'm wondering why one would expect a language model to know math. And I'm asking that because I think what a language model is basically is it's repeating stuff it has already seen, maybe with a bit randomness. This is how it gets like the creativeness we see, which is probably also hurting in solving math tasks. But I would expect, and this is maybe also similar to what you saw in your results, that numbers, shorter numbers, would appear more frequently in the data, and longer numbers would relatively appear less frequently in the data, and thus it is also less good in these because it hasn't maybe seen the same amount of example tasks for the long numbers compared to the short numbers. Yeah, I don't know. Does that make sense?
Yeah. No, it's an excellent question. In fact, it's quite the kind of question that I expected to receive, which I tried to address in this slide, but probably I was moving too fast. So you and I are exactly on the same page. I don't even know why we had to work on this paper, in the sense that it's obviously that multiplication is not, or I should say transformers are not the right modeling choice for multiplication, and there are limits in these things. Except people tend to believe, actually, people out there tends to believe that these days anything is so possible, to the point that they cannot possibly believe the results of our paper, and even question us back that there are other papers that says that these things absolutely can work. I mean, if you look at this, transformers absolutely can learn through multi-step algorithms in context and generalize to arbitrary problem sizes. And this paper was also about multiplication, and people come away with this impression that anything is possible. And when I talk about the results of this paper, a lot of scientists, well-known scientists, are genuinely surprised by the relatively low performance of GPT-3, even after supervised training, as well as GPT-4's relatively low performance, even with the scratchpad. There's something about the community's reaction. So I'm not saying everybody is thinking that way, but I found that perhaps I should say the community is very divided right now, with this ultimate belief about what transformers can do, and then a lot of skepticism. And I'm probably somewhere in the middle. Probably it's boring to say to somewhere in the middle, but I'm gonna be boring And I'm gonna be somewhere in the middle because I do think that these large models can be amazing. It's just that there are fundamental limits as well. And I'm just curious what those limits are. And this paper was trying to nail that down. The other takeaway message more broadly though is that, okay, maybe you and I agree that there's something odd about multiplication, for transformers. But now the question is, what else is odd? Like, because some of these common sense problems, failures that we saw later in the talk about, how many hours does it take to dry how many clothes? Why is it that it looked like it was fixed, but it's not really fixed? And is that really correct way of doing things, like RLHF at scale, fixing all these error cases one by one? Is that the correct way, even if it's not multiplication and it's based on language? Is that really correct way? And I feel like maybe it's not correct way. Maybe there's a better way. I don't know what that is, but this feels like whack-a-mole and it seems incorrect way.
All right, thank you so much, Yejin, for the great talk.
Thank you so much. I really wish I can somehow magically heal by tomorrow and then hang out there. We'll
All right,
see.
okay, I wish you a quick recovery. And for the other people, remember that we have the banquets today at 8 o'clock. You can find the map in the website. You can either walk there, it will take what, half an hour, 40 minutes, or you can take the subway or an Uber, whatever you prefer. So I hope to see you everybody in the banquets. Thanks.